Welcome back everyone, this is Introduction to MRI Physics Part 2. So why the Terminator? Why not? All the images here has been fully de-identified to protect patient's privacy. The first lecture we talk about signal generation. Let's go through the second step to form an image. As we mentioned before, there are a couple of steps we need to do to form an image. First of all, you need to have signal. So having signal itself is not all that useful if you cannot tell where the signal is coming from. Also, you need resolution. Specifically, you need to have good spatial resolution and contrast resolution. In certain exam, temporal resolution. So let me give you an example of resolution. In this case, you have two sets of images. You have cis, Spinnego. Both of them are T2-weighted image. As you can see, CSF is bright. As you can see, there are bilateral CPA extractive masses. Even though both lesions are not that difficult to detect because of their mass effect, you can see in the T2 Spinnego, those two are much better seen because you have a better contrast between the lesion themselves and the compressed brain tissue. So the bottom image here, you have a better contrast resolution, which help us better visualize those lesions. Now, can you spot a third lesion? On the top images, you have much better spatial resolutions. Thickness is 0.7 millimeters. On the bottom image, it's much thicker. Within the Meckel's cave, you can see a third lesion. I think it's fair to say it shows up better on the top image because of better spatial resolution. So do you know what this patient have? Bilateral vestibular schwannoma plus another small schwannoma in the Meckel's cave. So an F2. To me, this second part lecture is much more difficult to grasp compared to the first one. So throughout the lecture, you may start to fade away and you may hallucinate some strange pictures in your head. Resist that temptation. And for junior residents, it's okay that you don't get a first try. Like me, it may take you multiple tries before you can start to understand some of this concept. But trust me, you'll get there. There are 3 steps of localization that we need to do. Slice selection, phase encoding, and frequency encoding. Some of this terminology I'm sure you have heard before on your rotations. In order to get there, we need to understand the concept of gradient. So you have a specimen in a machine, in this example 1.5 Tesla. Assuming that the entire field is homogeneous, all the protons from head to torso to feet should experience 1.5 Tesla. Plug the number into Lamarck's equation like we talked about on the last lecture. All the protons should be processing roughly at 64 from head to torso to feet. What if you have a linear gradient? In other words, you make the field stronger toward the head, weaker toward the feet. Now the subject is not experiencing a homogeneous field across. So their perception of frequency in the head region is going to be faster than the torso, then it's going to be faster than the feet. How do we generate a gradient? It's actually quite simple. You have 2 sets of loop coil toward each end of the MRI. And if you run the electricity in one direction, by running electricity through loop coil, you are producing electromagnet. If the direction is parallel to the main magnet B0, those magnetisms are additive. On the other hand, if you run the current in the reverse direction compared to the other coil, you would have magnetization in the opposite direction of the B0. That will be subtractive. Let's go into the center, the additional magnetic field strength will decrease. Right in the center, there's no gradient, so the proton in this isocenter will process at the original 64 MHz under 1.5 Tesla. And those 2 sets of coils create a gradient along the z-axis, so they are referred to as z-magnetic coils. And every machine has 3 sets of coils. Z coil, you have a Y coil, and you have X coil. And you can produce gradient in any direction if you turn on the combination of different coil, other than just X, Y, and Z. And right in the center, that's isocenter. That's where the magnetic field is most homogeneous. In general, all the clinical MRI comprise of a main magnetic field, and that's always on. It could be 1.5 Tesla, 3 Tesla. Then you have the XYZ gradient coil. In between, usually you have the shim coil. Closest to the body, you have the radio frequency coil. For those of you who wonder what shim is, shimming is something that you do in construction, where you make sure everything's level. Another example is that at the restaurant, if you have a table that's wobbling, the waiter can take a piece of paper, jam it under the leg, make sure the table is balanced again. That's shimming. I know most of us know this, but the main magnet of MRI B0 is always on. You don't turn it off when you go home? Unfortunately, MRI-related accident still occurs too often. MRI safety is no joke. This happened not long ago. In 2018, someone was killed by MRI carrying a MRI non-compatible equipment. That person was mistakenly told by the assistant, "There's no patient inside, the machine was not on." So once you acquire a signal, now let's talk about the concept of localization. The first step is the easiest one to understand, slice selection. If you think about CT, the concept of slice selection is very easy. Let's say you want to focus a thin section down the middle of the torso. It's easy. You have a source for photon and you have a detector on the other side. You just shoot the beam across. It can collimate the thickness of the slice, and that's your slice selection. If you want to have a slice in the other part of the body, you can physically move the patient to the region of interest, or you can move the source of the X-ray. Slice selection for MRI does not work the same way. So let's say you want to do the same thing. You want to have a slice selection in the middle of the torso with MRI. You have a patient in the tube, and it's 1.5 Tesla. At this point, all the protons are processing at 64 from head to body to toe. All the protons are processing at the same frequency, 64. If you send in a resonance pulse at 64, you excite all the protons across the entire body. So the signals come from everywhere, not just from the slice that you wanted. So there's no slice selection. How can we do that then? This is where the gradient comes in. Now you turn on the gradient. In this example, stronger to the head, weaker to the feet. Now the protons are processing at different speed based on Lamar's equation. Faster to the head, weaker to the feet. Now all you have to do is send in a same pulse again. This time around though, the one would resonate is the one that has the same frequency as the RF pulse that you just sent it in. Now the signal generated is coming from the slice that you wanted. What if you want to scan different region? You can calculate the precession frequency of the region that you wanted. In this case, let's say 70 megahertz. So instead of sending 64 megahertz, now you're sending 70 megahertz. Even though the entire body is exposed to the same RF pulse, the only part that will resonate is the slice that you selected. That's how you do your slice selection. It is physically impossible to have infinitely small frequency. So you need to give a range of frequency. That's another term that you have heard before. That's a bandwidth. So you have transmission bandwidth or you have receiver bandwidth. In this example, instead of just one single frequency, you send in a narrow bandwidth. Any proton that's processing at that range will resonate. Let's present in a different graphic form. Initially, you start off with no gradient. Let's say you turn on the gradient. The highest precession frequency toward the head now is processing at 74. The lowest precession frequency toward the feet is running at about 54. Again, the number is not real, just for illustration purposes. And you send in a bandwidth. That's how you decide the slice thickness. Right? In this case, 63 to 64, all the protons fell within this range will resonate. So you have a slice thickness. If on board exam they ask you, how do you change the slice thickness for MRI? Unlike CT, you just change the collimator to determine the slice thickness. In MRI, there are two ways you can do it. One, you can increase the bandwidth. So if you increase the range of frequency, if you double your bandwidth, you could double your slice thickness. What if you don't want to do that? What if you want to keep the same bandwidth? Another way you can do is change your gradient. If you make the gradient less steep, then you increase slice thickness also. So this is a question that's coming off directly from RSNA module. If the magnetic field gradient decreases, what will happen to the slice thickness? That's A, thicker. So there are two ways to change slice thickness in MRI. So that's the first step, slice selection. I think it's fairly straightforward. Now you have a first step of localization. You have the slices that you wanted. All you get is a signal coming from the entire slice. You have no idea if the signal is coming from the top, the bottom, left, or right. What if, for example, you want to detect a lesion like this little terminator in the right upper quadrant? How do you do that? This is the last two steps of the localization comes in. The frequency encoding step and the phase encoding step. So what you do is you create a grid system. Then you can tell the location of the signal that's coming from within the slice that you just selected. So you need to have a phase encoding, you need to have a frequency encoding. They are 90 degrees to each other and their direction is interchangeable. That grid system, as you know, is referred to as matrix. Before we get to frequency and phase encoding, let's briefly define frequency and phase. The best way to imagine is stopwatch. So let's start with scenario number 1. No gradient. Gradient is off. In this example, we have 3 groups of stopwatches separated by 3 columns. Columns 1, 2, and 3. Let's imagine that they are all powered by magnets. And as a group, all 6 of them forms a single signal. More in sync or in phase they are to each other, stronger the signal they will generate together. All of them now experiencing the same magnetic strength between column 1, 2, and 3. The clock will start to run at same speed in same phase. Phase means that the position of the hand, 12 o'clock, 6 o'clock, 9 o'clock, etc. If there's no gradient, the frequency between column 1, 2, and 3 will be the same, and they are also in the same phase. At this point, you will get the strongest signal because everybody is in phase. Scenario number 2. You turn on the gradient and the gradient stays on. Initially, column 1, 2, and 3, everybody has the same frequency and same phase. Now you turn the gradient on. Column 1 is experiencing the strongest gradient, column 3 the weakest. Therefore, the clocks in column 1 would have highest frequency and column 3 the lowest. The frequency is different. 1 is much faster than 2 than 3. But notice the phase is also different. So the entire group is completely out of phase. This group has the weakest signal. So if you turn on the gradient stays on, you would have caused a frequency shift and phase shift. Different frequency, different phase. Let's take a look at scenario 3. We turn on the gradient stays on briefly, and you shut off the gradient. Initially, there's no gradient, so column 1, 2, 3 have the same frequency and same phase. And you turn on the gradient, the frequency is different and the phase is different. So column 1 is faster than column 2 than column 3. What if you shut off the gradient? Now the frequency are the same again because the magnetic field strength is exactly the same, so they are all going to run at the same frequency or the same speed, but the phase remains different. So the key point here is, if you want to produce a frequency shift, so different columns have different frequency, you need to turn the gradient on, and the gradient must stay on the whole time. Because if you shut off the gradient, their frequency will be the same again. If you want to cause phase shift, you need to turn on the gradient first to make sure that they are out of phase with each other. Once that's achieved, gradient is no longer needed. The phase shift has already occurred. So this point is very important. So if you don't understand the concept, please rewatch this segment again. Now let's say you are listening to a chamber ensemble that's comprised of 6 terminators. They'll play violin at exactly the same frequency. You close your eyes. all you hear is one chunk of music coming toward you at exactly the same frequency. You were not able to differentiate based on their frequency where the signal is coming from, because all the frequencies are the same. What if, as a conductor, you ask column 3 violinist to play faster and column 1 to play slower? So as a conductor, you turn on the gradient, weaker on the column 1, ISO column 2, stronger column 3. So now the column 1 would have lower frequency, column 3 would have higher frequency. Now you can start to differentiate based on their frequency differences. When you hear low frequency music coming toward you, you know it's coming from the left side of the orchestra. If you hear higher frequency music, you know it's coming from column 3. That's how you localize based on their frequency differences. The thing is though, you hear the music coming toward you, they don't come at you individually as a small component of music. The music will come together toward you as one large chunk that complies with summation of the different frequency, forming this relatively complex looking wave. So you have high frequency signal, medium frequency signal, and low frequency signal. When they play together, they are additive and they form one complex signal coming toward you. Luckily, your brain has the ability to tease component signals out, and you are able to separate where the signal is coming from. So this complex wave can also be break down into component signal. This process of decompose a function into its constituent frequency is called Fourier transform. You have a particular slice selected. Now you want to localize the signal based on which column is the signal coming from. What you need to do first step is frequency encoding. In this example, along the x-axis. So when you look at the symbol diagram, remember initially give a 90-degree RF pulse. You have a signal that's quickly decay-free induction decay. And in span echo, you give a 180-degree recovery RF pulse, and you generate an echo. You know exactly when the peak of echo will occur. That's time to echo, or TE. It's twice the distance between 90 degree to 180 degree. You identify peak of the echo, then you sample the echo symmetrically before and after the echo peak. So you start with slice selection. You turn on the gradient in the frequency encoding direction. How many types you want to sample determine how many columns you want to generate. In this sample example, we're going to produce 16 columns. We sample the echo in 16 steps across a signal that's symmetrically increase in signal intensity, reaches a peak, and decrease. The thing is that when you're sampling the echo, you're sampling across time. You're sampling from time 0 all the way across an echo. So the frequency gradients turn on, and each column consists of different frequencies, from low frequency to high frequency. When the signal come back, they come back as one summation complex signal wave. So we need to find a way to break this complex signal wave into their component frequencies. So we do Fourier transform. After you do a Fourier transform, you can break them into their individual component frequencies. So in this case, column 1 will have the lowest frequency. The other end of the echo, you have highest frequency. Now you can separate the signal based on their differences in frequency. If you see the proton encoded with a low frequency, you know that it must come from column 1. If you detect the proton with highest frequency, then you know that it's coming from the lost column 16. So that's encoding the signal based on frequency differences. Confused? It's not a straightforward concept. Let's see if we can present it another way. Maybe that will help you or confuse you further. Well, let's say you have multiple images that you want to scan more inferiorly, and this is the image that you wanted. You have selected this cross-sectional image across lower extremity. Now, you're sampling across from the right leg to the left leg. The signal intensity is based on how much tissue you have at a particular column. So as you sample across time, the first couple columns, the signal intensity is essentially 0 because there's no tissue, just air. Signal increase and decrease based on how much tissue there is. Down the middle, again, no signal because there's only air. Then you're going to experience more signal again when you encounter the left leg. Let's say you want to differentiate the signal come from A versus B. How can we do that? Before the gradient, the entire field is homogeneous. In this case, 1.5 Tesla. So all the protons, whether it's in point A, point B, all the protons are processing at 64 megahertz. If we plot a graph with the x-axis instead of sampling time, change that into frequency. So you have a low frequency on one side, higher frequency on the other side, and right in the middle is, say, 64 megahertz. So let's keep the y-axis the same, is the signal amplitude. What do you think the graph should look like? Does it look like A, B, or graph C? Think about that for a second. If you pick graph B, you are correct. Does that make sense? Remember, all the protons in this cross-section are processing at the same frequency. There's no gradient, so everybody is processing 64 megahertz. Therefore, all the signal that's going to show up is at 64 megahertz. This type of graph is only useful in telling you that there's a positive signal. It tells you nothing about its location. Do we even use this in radiology? The answer is actually yes. That's how spectroscopy does. Remember, with spectroscopy, you just put a region of interest. You don't really care where the signal is coming from. It's all coming from the same voxel. But for anatomical imaging, this is essentially useless. Now we turn on the gradient. In this example, you have a gradient stronger toward the left leg, and it's weaker toward the right leg. So the proton at point A would experience a lower magnetic field compared to proton B. Proton A would process at a lower frequency than proton B. Now you will have a graph that looks like this. For example, proton A is processing at 62 megahertz. So all the proton that's processing at 62 megahertz in the same column will be plotted based on signal intensity. At this point, at 64 megahertz, that's right on the isocenter where there's no proton, air. There's no signal at 64 megahertz. At point B, let's say it's processing at 66 megahertz. So all the protons processing at 66 megahertz will be plotted into its proper frequency, giving you a graphic look like this. If you assign the signal amplitude to the grayscale, the higher signal is going to be wider. When there's no signal, it's going to be pitch black. That's starting to resemble the anatomical picture. So now you can tell the signal is coming from column A versus column B. But you do not yet have the ability to differentiate between different points within the same column, point A and point C. Now you have to separate them into different rows. So that's a third step, phase encoding. Again, not the easy concept to get. Confused?
Start to hallucinate different things?
It takes most of us multiple tries before the idea can sink in. So let's talk about phase encoding. After you go through frequency encoding step, you establish 16 different columns. Now they are able to localize the signal based on their unique frequency between different columns. So you've done your frequency encoding, so you have a matrix of 16. Let's say you want to have a 16 by 16 matrix. You want to do 16 different phase encoding, producing a matrix of 16 by 16. So you want to establish different rows. How do we do this? How do we separate a signal between row I, E, and row A? The answer is also you use gradient. As an illustration, let's say you have a two group of tissue. Initially, everybody's in phase. So if you take the whole thing as a group, when they're in phase, you have the highest signal. As you increase the gradient, The one in the top row is experiencing the strongest magnetic field, therefore you're going to experience the highest phase shift. If you use the entire group to generate signal, the signal will decrease because they are not in phase. When you apply another gradient that's even stronger, you will induce even greater phase shift. As a group, you're going to experience even more signal loss. So stronger the gradient, stronger the signal loss you will induce. So between row I, E, and A, initially when there's no gradient, all the protons are in phase and you will get the least amount of signal loss. You sample the signal from the echo, then you register the signal right in the center row I in this example. And then you start off with a smaller gradient, you induce a small degree of phase shift and small signal loss. Then you place this data further away from the center row in row E. As you increase the phase encoding gradient more and more, now you're inducing maximum phase shift and maximum signal loss. You then place this data in the most outer row, furthest away from the center in row A. You can do the same process, smaller gradient, smaller phase shift, place that slightly away from the center, maximum gradient in the other direction, you induce the maximal phase shift and maximum signal loss, and you place that furthest away from the center at the other end. So how many times you're going to do your gradient is dependent on how many steps or how many matrix you want to induce. In this case, you are trying to do a 16 by 16 matrix. So you have 16 steps of frequency encoding and 16 steps of phase encoding. Let's look at it the other way. In this case, in the z-axis, you have overall signal intensity, and you're sampling across an echo. And the signal will get stronger, reaches a peak, and decrease symmetrically in the shape of the echo. And you sample across time, and you have finished your frequency encoding. So you have not induced a phase shift yet. So your signal profile will look something like this. You have a symmetrically increasing signal intensity, reaches a peak, and symmetrically decreasing signal intensity, a signal of an echo. Because you have not yet induced a phase shift, there's no gradient along the phase encoding direction. Every single row should have exactly the same signal profile. So at this point, you do not have a localization in the phase encoding direction. Now you induce a gradient, so you cause a phase shift. The center row will retain its original signal profile because right in the center there's no phase shift, so you have not lost any signal. As you're getting further and further away from the center, protons they become more and more out of phase as the gradient increase. So toward the edge, you see this group has the lower signal magnitude. And in the negative gradient, you see exactly the same profile. Further away from the isocenter, more phase shift they will experience, and therefore more signal magnitude loss they will experience. If you place those information into a datasheet, you would have a source image that look like this. At the isocenter, you have maximum signal intensity. Further away from the center, you are experiencing greater signal loss. This raw data, this source image, by the way, is the case space. Now let's try to put things together. In this pulse diagram, you have a 90-degree RF pulse followed by a 180-degree RF pulse producing an echo. As mentioned in part 1 of this presentation, you probably recognize that this is a spin echo because it has a 180-degree recovery RF pulse. Since we control the timing of the echo, we know exactly when the echo peak will occur at TE. We have the ability to sample the echo symmetrically before and after the peak of the echo. Now, how many measurements we want to take of the echo depending on what matrix size we want to have in the frequency encoding direction. In this example, we would like to have a matrix size of 16 by 16. So we need 16 frequency encoding steps in the x-axis and 16 phase encoding steps in the y-axis. So 16 columns and 16 rows. So we turn on the frequency gradient and sample the echo in 16 steps. Initially, we also turn on the highest phase encoding gradient. We then write this data in the row furthest away from the center. Then we repeat the process again, using the same frequency encoding steps and sampling the echo in 16 steps. The only thing we change here is the phase encoding gradient. We decrease the gradient a little bit. Then we write the second set of data in the next row closer toward the center. Then we repeat the process, Notice when it's at zero gradient, we place the data in the center row. That's why the center row has the highest signal intensity in the K-space. As gradient increase in the negative direction, we start to place the data in the row further away from the center in a mirror image fashion. That's filling the entire K-space. Just to review definition, some terminology, the time to echo, or the echo time, is from initial 90-degree RF pulse to the peak of echo, and the time interval between 90-degree and 180-degree RF pulse is half of TE. You sample and cross the echo. You waited for relatively a long time to let all the protons finish their longitudinal recovery. Now you can repeat the process all over again. All you do is just decrease the gradient in the phase encoding direction just slightly. Turn on your frequency encoding gradient. You sample the echo again, and you roll that in the second row. So the time between initial 90-degree RF pulse until the time you're ready to do it again, that's TR. As you can see, TR will always be longer than TE, usually substantially longer than TE. So one key point here is that TR is the time-consuming step, and T is not because it's usually very short. So each time you sample the echo, you write a single line, a single row, in the K-space. In order to fill the next line, you have to repeat the whole process, so you need another TR. As you can see, the process of filling one single line is very fast. So sampling of the echo itself is very fast. But you have to wait for a while before you can do it again. You have to wait for a while before you can fill in the next line with next TR. So in writing the next line in the K-space, wait for a while, repeat another TR, another TR, another TR, and eventually you will fill a single sheet of K-space and you have your data for one single cross-sectional image. Again, TR and the phase encoding step is very slow and time-consuming compared to TE and the frequency encoding step. Therefore, when you look at the equation of scan time, it's TR times the number of phase encoding step times NEX, number of excitation, or NSA, number of signal average. What's missing here is TE and number of frequency encoding step. In other words, TE and frequency encoding does not factor into scan time. TR, phase encoding, factor into scan time. So let's put things together one more time. We have done our slice selection step, and here we have a single cross-section slice, and we are going to sample the signal echo and to fill in the K-space. Initially, we have a complex summation signal as we sample the echo. We then do our phase encoding steps in the x-axis and Fourier transform. Now we can localize the signal based on their unique frequency in each column. Then we perform phase encoding steps in the y-axis and Fourier transform. We can now identify the signal based on its unique phase in each row. So different frequencies in different columns and different phases in different rows. Notice that the shape of the echo is such that the signal magnitude is the highest at the center, which is the peak of the echo on the x-axis. On the y-axis, the phase encoding direction, the center line, represents the group of protons that sees zero gradients or zero phase shift, therefore also has a higher signal magnitude in the center row. So in the center of the K-space, you are going to see brightest signal. In contrast, at the periphery of the K-space, you will see the lowest signal intensity. Eventually, the K-space is constructed into a final image slice. But K-space is how we choose to store the data collected. it does not have a one-to-one locational correlation to the final image. So this bright spot here, for example, does not translate into the center location of the final image. Even though it looks like there's nothing going on at the periphery of the K-space, it seems like all the action is concentrated in the center of the K-space. The peripheral region of the K-space contains important information about edge definition. In other words, how sharp the borders are between different structures will be on the final image. It's important for spatial resolution. Think about this. The sharper the gradient, more steps that you can fit in the phase and frequency encoding directions in the final image. Therefore, you would have higher matrix size. This information is represented at the edge of the K-space. At the center of the K-space, those data are important for the overall signal intensity and the overall contrast between different tissues. If you come across a question like this, that you have a K-space, you have a final image look like this, if the question asks you, there's a corrupted data in the center of K-space, all the data in the center of K-space has been lost, what's the resulting image look like? The choice that you don't want to pick is something look like that. Because as you know, K-space does not have a one-to-one correlation with what the final anatomical image will look like. It will not present as a loss of signal in the center of the final image. Instead, it will look something like that. You can see that the edge definition between different tissue, for example, the edge of the scalp, calvarium, corpus callosum, gray-white differentiation, the edge remains sharp. What's lost is overall signal intensity and the contrast information between tissues. On the other hand, if the correction occurs so that all the peripheral data is lost, the resulting picture will look like that, whereas the signal intensity and the contrast between different tissue, CSF, corpus callosum, remains intact, but what's lost is edge definition. So in other words, image looks extremely blurry. So the key point here is the center of the K-space represents contrast information and overall signal intensity, and the periphery of the K-space is important for edge definition, details, sharpness of transitions. Sometimes you can have a corruption in K-space. That's a K-space spike artifact. I know this concept is not easy to grasp, so the key point is the signal localization after you have a slice selection is based on their unique frequency and unique phase shift. The direction of frequency and phase can be interchangeable. So another key point, just to repeat, as I mentioned earlier, TR is always going to be a lot longer than TE, and phase encoding step is always much longer than frequency encoding, which is essentially just sampling across that echo. So naturally, phase encoding step affects scan time, whereas frequency encoding, because it's so quick, practically speaking, does not affect scan time. So scan time is TR times number of phase encoding step times NEX, number of excitation, or NSA, number of signal average. This question comes directly from RSNA module. If the phase encoding steps are reduced from 256 to 128, what will happen to acquisition time? So the key point, phase encoding gradient is a time-consuming step. Majority of artifacts such as wraparound artifact, motion artifact, ghosting artifact occur in the phase encoding direction. Because phase encoding gradient factor into scan time, you can understand that we usually choose it for the shortest anatomical dimension on the cross-sectional imaging. The long axis, we use frequency encoding because it's so much faster in that direction. Here you can see there are ghosting artifact from the orbit and there are motion artifact going in the left and right direction. So you know the phase encoding is in the direction of motion artifact. Also you can see the shortest anatomical axis is from left to right. We usually choose the phase encoding step in the same direction as the short axis. What about this question? First of all, the short axis through the abdomen is AP, but more importantly, the motion artifact, the ghosting artifact, is also in the direction of AP, so you know for fact the phase encoding is in the AP direction, and frequency encoding is left to right, or right to left. Remember though, they are interchangeable, so you cannot always rely on the short axis or long axis of anatomy. you have to look for artifacts to answer the question correctly. Now we're beating the dead horse. As you can see, ghosting artifact of the orbit is AP, so in this case, the anterior to posterior. What if you're following up on a lesion in the left medial temporal lobe that's been obscured by this artifact? A practical approach that you can ask your tech to flip the direction of the phase encoding gradient. The ghosting artifact will go, instead of AP, now you go from left to right, therefore opening up this area. The lesion no longer been obscured. That's one of the practical examples how MRI physics would affect our daily practice. So is everybody still awake? I realize that these are not straightforward concepts to understand. And for many of us, myself included, it will take multiple tries before it will start to make sense. So I encourage you to continue going at it, continue to read more, and listen to other people explaining the same concept. It will start to make sense. That concludes the second part of our lecture.